In this lesson, we are going to be solving quadratic equations that have complex solutions, and then we are going to be able to simplify expressions that involve complex numbers. In Algebra 1, when we took the square root of a negative number, we said that that was not possible in the real number system, and we spoke about the imaginary numbers. Well, this is where we're going to talk about those imaginary numbers. The square root of negative 1 is designated by the letter I. This is called the imaginary unit. And if we square the letter I, so I squared, that will be negative 1. The imaginary unit, I, can be used to find the square root now of any negative number. For example, if we want to take the square root of negative 16, we would actually separate that into two parts. Underneath the radical, we would separate that into the square root of negative 1 times 16. And then when we take the square root of the negative 1, that would be the letter I, and the square root of 16 would be 4. We can also do that with this example where we have the square root of negative 5. So again, we can break that into two factors, which would be negative 1 times 5. And the square root of negative 1 is our imaginary unit I, and then we can't simplify the square root of 5 any further. So our final would be I square roots of 5. So putting together the real numbers and the imaginary numbers, we come up with the number system called the complex numbers. Complex numbers can be written as A plus BI, where A and B are real numbers. A is the real part and the BI is the imaginary part. So if you take a look at the chart, we have some examples over here of real numbers, negative 1, 5 over 2, 3 pi, square root of 2, and so on. Then we have our imaginary numbers, which are pure, meaning there's no other part to that. For example, we just had a moment ago the square root of negative 16. That is negative 4i, or it could be positive 4i. Same thing with 6i. Then if we put a real part with an imaginary part, we have the imaginary numbers coming up together now. Joining all of those together are called the complex numbers. So let's take a look at some graphing that we would do with these numbers. So if we wanted to plot the complex number negative 3 plus 2i, if you'll take a look at the graph, the horizontal axis is designated for the real numbers and the vertical axis is designated for the imaginary numbers. We start at 0, 0, the origin on this coordinate plane, and if we're going to graph negative 3 plus 2i, we go left 3 on the real axis, and then positive 2i goes up 2 on the imaginary axis. If we wanted to plot the point 2, negative 3i, we would start again at the origin, and we would go to the right 2 on the real axis, and then down 3 on the imaginary axis, and that's going to give us 2 minus 3i. And then if we wanted to plot just the imaginary number 4i, we start at the origin 0, 0. We don't have a real part, so we won't go right or left, and we will simply go a positive 4i, which means up 4 units on the imaginary axis. Now we can solve quadratics, and we may end up with some now imaginary solutions. So the first thing we're going to do with this problem, we want to get the x squared by itself, is we're going to subtract 26 from both sides. So we have 2x squared is equal to a negative 36, and we're going to divide both sides by 2. So we'll have x squared equals negative 18. And then we're going to do the opposite operation, or the inverse, which then is to take the square root of both sides. So remember, a square and a square root are opposite operations, so they'll cancel each other. So we have x equals plus or minus. Now we want to simplify the square root of negative 18. The first thing that we would do is to separate the negative 18 into two factors of negative 1 times 18. And we can take the square root of each of these separately. So this is going to be the I portion. And then if we make a factor tree for 18, we have 9 and 2 and 3 and 3. So the 3, the factor pair, one of the 3's can also come out. So we're going to have 3i outside of the radical, and underneath the radical will still be the number 2. So our solution for this quadratic equation is plus or minus 3i square roots of 2. Let's take a look at the next problem. So we're going to subtract 1 from both sides. And so we have 9 times the quantity w minus 4 squared is equal to negative 1. And then we'll divide both sides by 9. So we have w minus 4, the quantity squared, is equal to negative 1/9. Doing the inverse operation, we're going to take the square root of both sides. And so since a square and a square root are opposite operations, they'll cancel each other. And we have plus or minus, and now we want to simplify this root. Again, we'll break that up into two pieces. We're going to take negative 1 times 1/9, and we're going to take the square root of each of the factors. The square root of negative 1 is I, and the square root of 1/9 would be 1/3. So we have 1/3 I as our simplified square root. To continue solving, we need to make sure to add 4 to both sides. So we have w equals, and we're going to write our complex number, making sure that our real portion is written first, and then our imaginary part. So w equals 4 plus or minus 1/3 I. Now we're going to practice combining like terms when we have complex numbers. So what we will do is make sure that we add the real portion of the numbers together, and then we add the imaginary part of the numbers together. So the real portion would be the negative 1 and the positive 3. Combining like terms, that would be 2. And then we will add the imaginary parts together, which would be 2i plus 3i would equal 5i. This is similar to when we would add 1 plus 2x and 3 plus 3x. So when we add those together, 3 plus 3x. When we add those together, we're combining like terms. We add the constant terms together, the 1 and the 3. And then we add the 2x and the 3x to get 5x. That's the same concept with the complex numbers, adding the real portion and the imaginary portion. So let's take a look at letter B. The first thing that I would do, and it helps me, is to distribute the negative sign. So I'm going to distribute that, making it a negative 3, and then a negative would make that a positive 7i. So when I add the real parts of these expressions together, 2 and a negative 3 would give me negative 1. And then when I add the imaginary portions, the negative 3i plus the 7i, that's going to give me 4i. In the next example, letter C, again, I prefer to distribute. Some of you may just be able to subtract both of those. This helps me to combine the like terms. So I have my real portions, which would be negative 3 plus 2, which would be negative 1. And then I'm going to add all my imaginary portions. I have 2i and a negative 1i, which would be 1i, and then a negative 3i, which is going to give me a final of a negative 2i. So I have negative 1 minus 2i. We can also use other properties with our imaginary and real numbers. So what we're going to do with our complex numbers is we're going to now distribute the negative I to our complex number. So negative I times 3 would give me negative 3i. Negative I times a positive I is going to give me a negative I squared. Now we need to simplify. So we have negative 3i, and remember that I is the square root of negative 1. So if I square it, this is actually a negative 1. So now I have minus negative 1, which would be plus 1. Then I need to write this in standard form. So when I write that in standard form as a complex number, I'm going to have 1 minus 3i. In the next example, we're going to do the distribute over the FOIL method. So I'm going to take 2 times negative 6, which is going to be negative 12, and 2 times negative 2i, which is negative 4i. Then I'm going to take 3i times negative 6, which is going to give me negative 18i. And then I'm going to take 3i times negative 2i, which is going to give me negative 6i squared. So to simplify, please remember that I squared is negative 1. So we actually have negative 12. Combining negative 4i and negative 18i together, that's going to give me negative 22i. And then negative 6 times negative 1 is positive 6. So writing in standard form and combining like terms, we have negative 12 plus 6 is going to give me negative 6 minus 22i as my complex number. Let's take care of letter C. I think we could take a look and know that they're the opposite binomials. So it's going to be similar to the difference of squares when we multiply. Let's use FOIL. So 1 times 1 would be 1, and 1 times negative 2i will be negative 2i. Then 2i times 1 is going to be 2i, and 2i times negative 2i would be negative 4i squared. Combining like terms, we can see the negative 2i plus 2i would be 0. Remember please that I squared is negative 1. So we would have 1, and then negative 4 times negative 1 would be positive 4. So 1 plus 4 would give me 5. In our next example, we want to write this quotient in standard form. To do that, we cannot have an imaginary number in the denominator of a fraction. So we want to get rid of that by multiplying by what is called the complex conjugate. So what we're going to do is take our expression, our rational expression, and we're going to multiply both the numerator and the denominator by the opposite of the denominator. So it'll be 1 minus I. And we do that to both the numerator and the denominator, and that will eliminate the imaginary portion in the denominator. So we'll start by foiling the numerator. We're going to take 2 times 1 and 2 times negative I. So we'll have 2 minus 2i. And then we'll take negative 7i times 1, which is negative 7i. And then negative 7i times negative 1, which would be plus 7i squared. Then we're going to multiply the denominator. So we'll FOIL it. We have 1 times 1 and 1 times negative I. So we have 1 and then negative I. And then we have I times 1 and I times a negative I. So that'll be plus I minus I squared. If you remember then, I squared is negative 1. So let's simplify the top. We have 2, and then 7 times negative 1 is negative 7. So 2 plus negative 7 would give me negative 5. And then combining negative 2i and negative 7i together, we have negative 9i. In the denominator, we have the I and the negative I have a sum of 0. And then negative and a negative would make that plus 1. So we have 1 plus 1, which would be 2. So that is the quotient written in standard form, where we've eliminated the I in the denominator of the fraction. Let's try another example. This time we're going to involve imaginary numbers as well as roots. So we are going to multiply both the numerator and the denominator by the complex conjugate in order to get rid of the radical as well as the imaginary portion in the denominator. So we'll multiply both by the complex conjugate, which is simply the denominator but changing the sign. So now we are going to use the FOIL method or distributive property to simplify. So we're going to take 3 times 2, which is 6, and 3 times I squared root of 5, that's going to be 3I square root of 5. Then we take I square root of 5 times 2, so that's going to be 2I square root of 5. And then we're going to multiply I square root of 5 times I square root of 5. So that's going to be I squared, and then the square root of 5 times the square root of 5 is 5. Now let's take a look at the denominator. So we're going to multiply 2 times 2, which is 4. 2 times I square root of 5 is going to be 2I square root of 5. Then we're going to multiply the negative I square root of 5 times 2, which is negative 2I square root of 5. And then we're going to multiply negative I square root of 5 times positive I square root of 5. So that's going to give me negative. I times I is I squared, and square root of 5 times the square root of 5 is the square root of 25, which is 5. Okay, so let's do some simplifying. First of all, I squared, if you remember, is negative 1, and when we multiply that by 5, we're going to get negative 5. Likewise over here, I squared is negative 1, but there is a negative sign here already, so that's going to make it a positive 1, times 5 will be 5. Combining like terms on the top, 6 minus 5 would be 1, 3i plus 2i would be 5i square root of 5. Since we're adding, remember, we only combine the leading coefficient and we leave the radical. And then in the denominator, the 2i square root of 5 minus 2i square root of 5 would be 0. And then 4 plus 5 would be 9. That is our simplified form of our original rational expression, and it is in standard form. The last thing that we're going to take a look at with our complex numbers is how do we find the absolute value of a complex number. As you can see in the definition, the absolute value of a complex number is denoted by the absolute value of z. It is a non-negative real number, and it's defined as a squared plus b squared, the square root. Now, that should look familiar to you. This actually is going to be the distance from the origin on the coordinate plane to the point that is graphed for the complex number. So let's take a look at a couple of examples. So we want to find the absolute value of each. So let's start with letter A. So what we're going to do to find the absolute value of 3 plus 4i is we're actually going to take a squared plus b squared, and then we are going to take the square root of that. So a is 3, b is 4, so we're going to take 3 squared plus 4 squared. 3 squared is 9, and 4 squared is 16. So 9 plus 16, that's going to be the square root of 25, and the square root of 25 is 5. That is going to be the absolute value of that complex number. So let's take a look at the second one. Negative 2i. There isn't an a portion, but the b portion is negative 2. So negative 2 squared is 4, and the square root of 4 would be 2. That means that it would be 2 units. And the last one, we have negative 1 plus 5i. So we're going to find a squared plus b squared. So a is negative 1, b is 5. So a squared would be 1, b squared, 5 squared would be 25, so that's going to be the square root of 26, which is approximately 5.10. Now what we can do then is to take a look on the coordinate plane. So our first one example, 3 plus 4i, remember we go 3 units to the right and 4 up on the imaginary axis. This is actually our point on the coordinate plane, and the absolute value of this point is actually this distance then from the origin. In our second example, we had negative 2i, so here was that point graphed on the coordinate plane. And when we found the distance, that would be actually 2 units from the origin. That's the absolute value. In the second example, we had negative 1 plus 5i. So when we found the absolute value of it, we got the square root of 26, and that is the distance from the origin. So let's review complex numbers. First of all, our imaginary unit, I, is equal to the square root of negative 1, and when you square that, you get negative 1. Complex numbers are a plus bi, where a and b are real numbers. Please remember that when you are adding or subtracting, you're only adding or subtracting like terms. And another important thing to remember is when you write the quotient of two complex numbers in standard form, you want to simplify by using the complex conjugate. Please remember to complete the reflection.